In this lecture, I will introduce set theoretic operations on combinatorial classes. Before we do that, let me just remind you that if we have a combinatorial class, then its elements come with a size, and we can talk about its ordinary generating function ax, and this is just sum n goes from 0 to infinity, uh, an x to the n, where an is the cardinality of an, which is the number of elements alpha in A, such that the size of alpha is n. And this has another form which we call the combinatorial form of the ordinary generating function. You can simply think of it as a sum over alpha in A, and then you take x to the power size of alpha. These two are clearly the same, and this sum here only makes sense if we have this condition that the size of alpha n is an is finite for every n. Then there will be only finitely many terms corresponding to each monomial, and so this uh, sum here will not make sense unless A is actually a combinatorial class, in the sense that it has satisfies the finiteness condition in the definition of a combinatorial class. Okay, and now let's look at some basic operations. So suppose A and B are combinatorial classes, then I will define A plus B to be the class with underlying set A disjoint union B. By which I mean that if A and B have any elements in common, you copy out those common elements to a second copy, and you treat them as different things. So you take the disjoint union of A and B, and I must still define the size. So if I have x belong to the disjoint union of A and B, then its size so I'll use the subscript to say where I'm looking at the size of an element. So x is either in A or in B, so it's going to be the size of x in A if x belongs to A, and it's going to be the size of x in B if x belongs to B. And that's the combinatorial class A plus B. And this name A plus B is suggestive because if C is equal to A plus B, then the generating function for C is given by, well, it's the sum over all alpha in C, x to the power size alpha. But C is a disjoint union, so this is firstly the sum over alpha in A, x to the power size alpha, and then secondly alpha in B, x to the power size alpha, which is the same as Bx plus Cx. So the generating function of the sum is the sum of their generating function. So this is called the sum of the classes A and B. Let's define the product of classes is the class with underlying set the Cartesian product. So that's just the Cartesian product of all ordered pairs A comma B, where A is in A and B is in B. And I must define the size. So if I have an element of A cross B, it's of the form alpha comma beta, where alpha is in A and beta is in B. I'll just define its size to be the sum of the size of alpha in A and the size of beta in B. And then we have that if C is A cross B, then C of X is sum over alpha comma beta in A cross B x to the power size of alpha x to the power size of beta, because it was just x to the power size of alpha plus size of beta. And I can then write this as a double sum. Alpha belongs to A, summation beta belongs to B, x to the power size of alpha x to the power size of beta, and that is nothing but ax times bx. And so the generating series, ordinary generating function, the product of classes is the product of their ordinary generating functions. And the last construction operation that I will be introducing in this lecture is the sequence construction. This is called the product, and now I'll be introducing the sequence of A. So this is defined in terms of sum and product. It's defined as, firstly, a singleton class of size, element of size 0. I'll call it the neutral structure, or the empty sequence of size 0. And then there'll be the class A itself, then there'll be A cross A, then there'll be A cross A cross A, and so on. One way to write it is that this is summation, n goes from 0 to infinity, the nth Cartesian product of A, where we take the 0th Cartesian product as just a singleton set. Now, one important point to note is that if there exists alpha in A such that alpha has size 0, then in here I can find infinitely many elements of size 0. Epsilon, then I can take alpha itself, then I can take alpha comma alpha in A cross A, then I can take alpha comma alpha in A cross A cross A. All these have size 0. Just because of the way size is defined in the product, it's the sum of the sizes of the components. And so this means that A0 is an infinite set. And so this is not a combinatorial class. So what we need is that, let's just add a condition here. Let A be a combinatorial class such that A0 is equal to 0. Okay, so this is the sequence construction. And what we have here is that if C is equal to sequence of A, then Cx is sum n goes from 0 to infinity ax to the power n. And this we've seen, this ax is going to be a formal power series with 0 constant term because of this condition that a0 is 0. The original A. Here what I mean is sequence of A. 0 is 0. But I have is infinity. But here I'm assuming that A0 is 0. That means the cardinality of A0 is 0. And so this will be a power series, AX will be a power series which vanishes at 0. Its constant term is 0. And so this will be convergent. And this can, in fact, we've seen that this is the same as 1 over 1 minus AX. Okay, now so these are going to be operations so that we can take simpler combinatorial classes and perform these kinds of operations and get more complicated combinatorial classes. But to start these constructions, we need some very basic combinatorial classes. Let me introduce two of them. So I'll call them the neutral class. The neutral class is the class denoted by E. It has only one element, namely epsilon, and the size of epsilon is 0. This is called the neutral element. So in this definition of sequence, I could have written this is epsilon plus a squared plus a cubed and so on. And the other very basic class that I want to introduce is the atomic class. The neutral class has something of size 0, but if you actually want to build non-trivial things, you want elements of size at least 1, and the atomic class is the minimal such thing. So it's denoted by x. It sort of corresponds to the variable x in our power series, and it has only one element, which we usually denote by a small circle, which may or may not be filled in. And the size of this object, this represents an atom. The size of the atom is 1. Okay, so let me show you how you can use these things to build classes. But before that, it may be a good idea to know when two combinatorial classes are essentially the same. So I'll define an isomorphism of combinatorial classes. An isomorphism of combinatorial classes A and B is a bijective function phi from A to B, such that if you take any element of A and you take its image under phi and you take its size under B, that is going to be the same as the size of the original element in A. So it's basically a size preserving bijection. And when two combinatorial classes are isomorphic, we'll think of them as being the same. And so now let me put all these ideas together and write down a statement. So remember, we had this combinatorial class W of binary words. I claim that W is isomorphic to sequence of x plus x. Why is that? Well, our alphabet A consists of two letters 0 and 1, and that is isomorphic to x plus x because both have two elements, each of size 1. And of course, W is, as we said, it's words in 0 and 1, so it is really sequence is of 0, 1, which is the same as sequences in x plus x. And let me give you another example of such an isomorphism. If we take the class C of all triangulations, then this is isomorphic to x cross C cross C. The proof that I had done earlier to show that triangulations satisfy the recurrence relation for Catalan numbers actually is giving a bijection between the class of triangulations and this product class x cross C cross C. And this implies that Cx is equal to x times Cx squared. So what you're seeing is that this identity here of generating functions comes from this bijection here of combinatorial classes. And we will be doing a lot of this. We will be translating between set theory and relations between generating functions and vice versa. And sometimes you can just see a relation between generating functions and then infer that there must be some sort of set theoretic bijection, and then the generating function itself will tell you something about the combinatorial object that it is counting.